So, following sort of all of this discussion about hypothesizing, about the quantized states of electrons, this guy, Planck, came along and he looked at actually an experiment from Einstein that was called the photoelectric effect, and this is actually one of the things that that got Einstein the Nobel Prize. The photoelectric effect is this really sort of simple idea where experimentally, if you take light uh, and you blast it onto the surface of, say, a metal here, and typically this is in vacuum, just to be really clean. Um, that's a vacuum of three U's. If you shine light on this metal surface, nothing will happen until you keep decreasing the wavelength of the light. So keep decreasing the wavelength, increasing the frequency of the light until you hit a certain threshold. Then all of a sudden, once you hit that threshold, you pop off electrons, and you can measure those electrons. And so Einstein discovered this photoelectric effect, that if you put in a certain wavelength or frequency of light, then you can get electrons to actually liberate from the surface of the metal atoms that line the experimental surface here. So Planck, this guy, not so long after, another quantum mechanics originator, came along and he said, well, this threshold that people were observing, and I should say that the threshold was different for different metals. So if you did this with like magnesium metal versus scandium metal versus lead or sodium, etc., the wavelength, the frequency required to get the photoelectric effect to occur was different for these different elements. Planck came along and he said, well, clearly then what we're looking at is that these different elements have different electrons with different energies in them. So again, getting back to this sort of staircase structure of electrons inside each of these atoms, or this sort of orbital structure. And he really came in and quantized this, and he said that, well, the energy then of a photon must be proportional to the frequency somehow. And he deduced, and we're not going to do it in this class, but if you take a physical chemistry or quantum mechanics class, you can derive this. He deduced that the energy of the photon is directly proportional to the frequency, but it was adjusted by this, this factor of proportionality called, that he named after himself, called Planck's constant. And Planck's constant is this really tiny number, which is 6.626 times 10 to the minus 34 joule seconds. It's less important that you know that number. I'll always give that to you. What's more important is you understand the relationship here between these two variables, because h here is just a constant of proportionality. It just makes the units work out. But really what this equation is saying is really simple but powerful, is that the energy of a photon is directly proportional to the frequency. So as the frequency of a photon goes up, so does the energy of that photon. And that should make sense, right? The frequency of, say, a violet photon is higher than the frequency of a red photon, which means the frequency of ultraviolet light has a higher energy than that of infrared light, which is why ultraviolet light and X-rays can cause damage to human skin. By the same analogy, we can sort of combine the equation that we saw before that related frequency and the speed of light and wavelength, combine those all together, and we can get a separate relationship that says E equals hc over lambda. And all we're doing here is putting this equation into the equation we had already formed before, and the utility here is telling us what we should already sort of know. Because we know energy and frequency are directly proportional, then we should know that energy and wavelength are inversely proportional. So as the wavelength goes up here in the denominator, then the energy of that specific photon goes down. So if you've got radio waves that have really long, sweeping, almost kilometer-long wavelengths, those are really low energy. based on Planck's relationship here. And so this is really relating the what people call the wave-particle duality of light. It's sort of thinking about photons of light as either these particles which can smash into a surface and liberate another particle, a subatomic particle, or it's relating it to the actual wavelength or the wave properties of that light. And so that was Planck's contribution to, among many, many contributions he made, this was a really big one that we're going to focus on in this class. Okay, so shortly after this, this really brilliant, actually graduate student named de Broglie, I'll write his name out for you. You don't have to memorize this, I just tell you for fun. This guy, de Broglie, or de Broglie, he was a graduate student at the time, and he was brilliant. He came and said, well, okay, so Planck says that light, the energy and the wavelength of light is related through this sort of proportionality. Einstein, through his own generation, had developed this notion of E equals mc squared, which we've all learned about. We're not going to focus on in this class, but it's a key expression that that de Broglie used. So he combined these expressions, and I'll actually rewrite this this one. I'll just switch these two algebraically, so this becomes wavelength equals hc over E. If we combine these two expressions together, we could get this expression lambda equals hc over mc squared. The c would cancel here, and we would get lambda equals h over mc. Because c, as we've talked about, is the speed of light, what de Broglie did is replace the speed of light, because here we're talking about matter instead of light, the wave-particle duality of matter. He replaced this with the velocity of that matter, of whatever that was, if that was a particle or a chunk of matter or a human or a car, whatever it was. And so if we simplify this, what we get is the wavelength of matter is equal to, again, Planck's constant h over mv. And so here we have Planck's constant. This is the mass of the object, and this is the velocity of the object, and this is the wavelength of the object. And so we're not talking about light anymore. This is sort of generally called de Broglie's equation. We're not talking about light, we're talking about matter. So this is a big difference. We just got done talking about how Planck was the one who sort of reinforced the wave-particle duality of photons, which is a little bit easier for us to handle. But de Broglie came in and he said actually all matter, all particles could be thought of as either a particle or a wave, and he derived this expression. And really, this has huge implications. This states that all of the particles inside of an atom aren't just these points in space surrounding a nucleus in an orbit, but in fact they're actually these waves that could be modeled as sinusoidal waves just like a photon. And we'll talk about the implications of that. And it's not relegated to just small particles. Really, all of matter can be thought of or modeled as either a particle or a wave. That includes a human. So huge, huge, huge humans, if this number gets really big, right, if the mass of the object gets really large in the denominator, then the wavelength gets really small in this case. And so humans have our own wavelengths. Cars, trains, automobiles, they all have their own wavelengths that can be modeled simply by de Broglie's equation. But the wavelengths get so tiny that they're really unrealistic. And so if we have tiny masses, things like an electron or a proton, then we start to have wavelengths that are reasonable and interesting in how they might interact with photons of light that impact that sample. So the big contribution from de Broglie is that these electrons in this atom can actually essentially just stand as waves inside of the atom. Instead of zipping around in these predestined orbits like we think about in planetary science and stellar science, in fact they're just standing stagnant as waves that are oscillating up and down, and we call those standing waves. And that's a totally different way to think about the atom compared with the Bohr model that we just talked about. And so a standing wave, and I'll show you a video here in a second, is sort of like if you had your hand affixed to a rope here and you applied some sort of whipping action, you would get this thing to sort of whip up and down like this. That would be sort of a standing wave. And so the picture to the right is also a standing wave. Let me show you a video really quick to give you a sense for how we should think about electrons inside of an atom, because that's really what we're modeling here. These waves, these sinusoidal waves, are really just the shapes of electrons inside of that atom. So this simulation you can grab from your textbook. This comes from the same simulation we've shown a few times from this PhET group. What we can do is just imagine a rope here that is fixed at one end and that we can move in the other. And this is really modeling what a standing wave could look like, which is really just a proxy for what these tiny electrons behave like inside of an atom. So let's oscillate this thing. So this is a standing wave. You could imagine this is a standing wave between 2 points, but if we connected the beginning and the end together in a circle, now you have an actual electron wave inside of an actual atom. And you can change the amplitude of this wave or the frequency of this wave depending on the de Broglie equation and the specific energy level that that electron might have, right? If that's a high energy electron, we know that energy and frequency are related to each other in a linear way, and so we end up having really, really high frequency type waves. So as I mentioned before, if we take that standing wave, which is the model of what the electron should look like, and we connect the tip and the tail together, what we end up with is this sort of standing wave shape that's surrounding whatever the nucleus is in the center, where the wavelength is still defined as the distance between these two troughs. Depending on the energy and the wavelength and the frequency of that particular electron, it can overlap with itself constructively or destructively. Destructively means it starts to cancel itself out. And that's what gives rise to certain places in the atom where the electron can be and where the electron can't be. And that's what we get with these sort of discrete or quantized energy levels. If you have places where the standing wave overlaps constructively, then that's a place where the electron can exist. If you have a place where the electron at that frequency destructively interferes with itself, then it cancels itself out and an electron can't exist there. And so you can imagine in a real atom, instead of a bunch of electrons zipping around as particles, what we have are a whole bunch of standing waves, these sort of three-dimensional spherical standing waves, all superimposed on top of each other, going back and forth and in and out and in and out, where the only standing waves that exist are those that aren't destructively interfering. And each one of those waves is now this new n or orbital level that we're talking about. And we're going to call these things wave functions. We're going to give them this Greek letter psi. Wave functions are the possible places really places and or energies that an electron can take, and they're really derived based on this three-dimensional quantum wave mechanics math. And so if you go on to take a quantum mechanics course, or if you go on to take a physical chemistry 2 course in our department, you'll do some of the calculus required to actually model these three-dimensional waves and how they can constructively or destructively interfere, and you'll use these wave functions to compute the energies of the electron. We're going to hand wave this a little bit, but we're still going to talk about what the implications of this model is on our new understanding of how electrons exist, or the electronic structure exists in an atom.